Welcome back to another deep dive. Today, we're digging into something that's, well, it's on everyone's mind in AI, right?
Definitely.
What's the real environmental cost of these large language models we use constantly? We hear so much about training, huge energy costs there.
Oh, yeah.
The training footprint is massive, no doubt.
But what about after? When billions of us are actually sending prompts, getting answers back, the serving, the inference phase, getting solid numbers on that has been really, really tricky.
It's been a huge blind spot, honestly. And that's exactly why this new paper from Google is so important. It's called Measuring the Environmental Impact of Delivering AI at Google Scale.
Okay.
And it gives us the first sort of comprehensive look, real methodology, real world data on energy, carbon, water use for AI inference in a massive production system.
So not just theory, but what's actually happening.
Exactly. And for those of you wanting the quick version, the headline numbers, listen up. Using this really thorough full stack approach, they found the median Gemini app's text prompt uses just 0.24 heart-watt energy.
Okay, 0.24 watt hours.
Tiny. And it generates only 0.03 grams of CO2 equivalent and uses just 0.26 milliliters of water.
Wow. Okay, let's unpack that. 0.24 watt hours. That's what, like watching TV for maybe 9 seconds? Less energy than that even.
Yeah, basically negligible on its own.
Yeah.
And the water, 0.26 milliliter. That's like 5 drops.
Five drops of water. That is way lower than some numbers I've seen thrown around. Some estimates we're talking tens of milliliters.
Orders of magnitude lower, yeah. And what's really impressive, maybe even more so, is the progress they've made.
Right, the improvement.
Yeah, through better software, clean energy buying. They cut energy use for that medium prompt by 33 times. And the carbon footprint, down by 44 times.
In just 1 year.
In a single year. It's staggering. So this paper is not just about the numbers. It really underscores why we need this kind of standardized, comprehensive measurement. Otherwise, how can you compare models fairly or, really push for efficiency across the whole system?
Absolutely. And you touched on something key there, the measurement itself. For a while, everyone was focused on training energy.
Right, because it's a big upfront hit.
Definitely energy intensive. But now, with generative AI everywhere, these models answering billions of prompts, the ongoing operational costs, the inference part, that's become, well, potentially the bigger slice of the pie long term.
It really has shifted the focus, or it should have.
And measuring that inference piece,
Yeah.
before this paper, it felt like the Wild West. Super rough estimates,
Totally. Early guesses were based on high-level hardware specs, model size, just broad assumptions. I remember seeing figures for one GPT 3.5 prompt around 3 watt hours, a huge range.
Yeah, exactly. And even when people started trying to measure it empirically with tools like Code Carbon or Zeus.
Which was a step forward.
For sure, but the methods were all different. You'd get 0.3 for a GPT-4o prompt from one group, and then another saying maybe 1.8, even up to almost 7 WH for something similar. It was all over the map.
And water use, even crazier. 10 to 50 millil per GPT-3 prompt in one study. Mistral AI saying 45 millimil for theirs. Even when someone like Sam Altman shared numbers, I think it was 0.34 watt water, 0.3 LML for ChatGPT.
Right, I remember that.
But they didn't say how they got them. No methodology. So you couldn't really compare apples to apples. It was impossible.
Which brings us right to what this Google paper calls the measurement boundary problem. What exactly are you including in your calculation?
Yes, that was the missing piece. We needed transparent first-party data, sure, but also agreement on the boundary. What gets counted?
Because think about it, most older approaches, they just looked at the active AI accelerators, right? Just the chip power, basically, when it's working hard.
The obvious part.
But Google's saying, hang on, that's not the whole story. Their comprehensive approach adds in the host CPU and DRAM energy, the stuff supporting the accelerator.
Which makes sense, it's part of the system.
Then there's the energy used by idle machines, the ones kept ready for reliability, low latency. They're still drawing power even when waiting.
A significant factor, often ignored.
And then the whole data center overhead cooling, power conversion, captured by that PUE metric, power usage effectiveness.
Right, and if you leave all that extra stuff out, your numbers look way lower. But are they accurate? Are they comparable?
Probably not. The paper shows this really clearly. For a similar model, say Llama 3.170B, different measurement approaches could give you a 6-fold difference in how many prompts you get per kilowatt hour.
6 times.
Yeah.
How can you compare efficiency like that? You can't. So Google's goal here is to enable that meaningful comparison to push everyone towards looking at the whole picture for efficiency gains.
Okay, so let's get into their method. How did they actually do this full stack approach? What does it entail?
Right, so they designed it to be consistent, comprehensive, a standard for measuring energy, emissions, water for these big production AI models.
Got it.
For energy, they break it down into 4 main parts, and their Gemini data shows the breakdown. The biggest piece, maybe unsurprisingly, is the active AI accelerator energy. That's about 58% of the total watt hours per prompt.
So the chips doing the actual AI work pre-fill, decode in the transformer?
Exactly. And importantly, these are direct measurements from their live production systems, not simulations.
Okay, 58%. What's next?
Next up is active CPU and DRAM energy. That's around 24%. This is the power for the host machine's brain and memory, basically, needed to run the accelerators.
Another chunk that might get missed in simpler estimates.
For sure. Then number 3, and this is really interesting, idle machine energy, about 10%.
Okay, this is the power used by machines waiting for work.
Precisely. The accelerators and their host systems that are provisioned but temporarily idle, ready for spikes, ensuring low latency, they're still consuming power.
That's a crucial insight for production systems.
Absolutely. And the last piece is overhead energy, about 8%. This is the data center infrastructure cooling, power distribution losses captured by that PUE metric. And Google's PUE is impressively low, 1.09 fleet-wide average.
Wow, 1.09 is incredible. That's only 9% overhead beyond the IT equipment itself.
It's world-class efficiency.
And they were clear about what wasn't included, right? Like external networks, user devices, stuff they don't control.
Right, makes sense.
Yeah.
And obviously, LLM training wasn't the focus here, just inference. Method-wise, they collect power readings from the power supply units, track total machine time versus idle time, and divide by the prompt count over like a day or more for accuracy.
Very methodical. What about carbon emissions? How did they calculate that?
So that's based on the local grid energy mix where the data center is. Plus, they include embodied emissions from manufacturing the hardware.
Embodied emissions, too. That's quite comprehensive.
It really is. They use market-based emissions, MB, which lets them account for their clean energy purchases. And you can see the impact. Their MBE emission factor dropped from 135 grams CO2 equivalent per kilowatt in 2023 down to 94 in 2024.
Despite using more electricity overall, presumably.
Likely, yeah. It shows their clean energy strategy is working. And including those embodied Scope 1 and 3 emissions is pretty rare in other studies, makes this much more complete.
And water, how is that measured?
They use water usage effectiveness, WE Category 2, which tracks consumptive use water evaporated mainly for cooling that doesn't return to the local source. Their WUE was 1.15 liters per kilowatt for 2023 and 2024.
Okay.
And they mentioned they only consume about 80% of the water they withdraw, suggesting good management. Plus, they're actively shifting to air cooling where water is scarce.
Which has a broader sustainability focus.
Definitely. And one more detail on their method, why they use the median prompt energy, not the average or mean.
Ah, right. Why is that important?
Well, think about it. You might have a few outlier prompts. Maybe they hit a less busy machine or generated a ton of text using way more energy than usual.
Okay.
If you averaged everything, those outliers would drag the average up, making the typical experience seem worse than it is. The median, though, finds the middle value. It's not skewed by those extremes.
So it gives a better picture of a typical user prompt's impact.
Exactly. Much more representative for this kind of skewed distribution. It's a subtle but important choice for understanding the real-world impact.
Okay, so with all that careful methodology, let's revisit the core numbers for Gemini again. May 2025 data.
That's right. The median text prompt, 0.24 weight energy,
Tiny.
0.03 GCO2e emission,
Even tinier.
and 0.26 milli water.
5 drops. Okay. And how does this compare if they hadn't used their comprehensive method?
Great question.
Yeah.
They actually calculated that. Using an existing approach, similar to older, narrower methods, the energy would have looked like just 0.1 wide white per prompt.
Wow, less than half.
Yeah, their comprehensive method shows the energy use is actually 2.4 times greater than what that limited, idealized approach would suggest. It really proves why you need that full boundary.
It absolutely does. And just putting those numbers in context again, 0.24 white, less energy than watching 9 seconds of TV, 0.26 millimel, 5 drops of water. It really reframes things compared to those earlier, much higher estimates.
Completely. And the paper suggests 3 reasons why their numbers are so much lower than many public estimates.
Okay, what are they?
First, in situ measurement. They're using real data from real users in their actual production system, not a lab benchmark. That's way more precise.
Makes sense. Real world versus theory.
Second, model efficiency. Google's production models, like Gemini, they're probably right at the cutting edge, the Pareto frontier of efficiency. Highly optimized, unlike maybe some open source models used in benchmarks that haven't had that level of tuning.
Right. They're built for this scale.
And third, production optimization. Their whole inference system is just incredibly optimized. Things like efficient batching, grouping prompts together that you often don't fully replicate in isolated benchmark tests.
So real-world systems are just different.
Exactly. The scale allows for optimizations you can't easily do in small experiments.
And these aren't static numbers either. You mentioned the dramatic improvements they made.
Oh yeah, it's pretty wild. Between May 2024 and May 2025, that 44x reduction in total emissions per median prompt. It wasn't one thing.
No silver bullet.
No, it was a whole bunch of things compounding. They broke down the energy reduction to 33x overall from software efficiencies alone.
Okay, 33x. How?
Well, 23x of that came just from model improvements, better architectures, better algorithms,
Right.
and another 1.4x came from just using the machines more efficiently, better utilization
So model improvements were the biggest lever there.
by far. And then layered on top, you had the cleaner energy mix, reducing the carbon intensity and needing fewer machine hours overall, slashing the embodied emissions impact per prompt. It's optimization across the board.
Let's dive into those specific strategies. You mentioned smarter model architectures. What does that mean in practice?
So Gemini uses the transformer architecture, which was already elite, but they've refined it. A key technique is mixture of experts, MOE.
Right, MOE. Explain that a bit.
Imagine you have a huge model, but instead of using the whole thing for every prompt, you have specialized experts within it. For any given prompt, you only activate the few experts best suited for that task.
So you're only using a small fraction of the model's compute power each time.
Yeah. Exactly. Reduces computations by like 10x to 100x. Huge efficiency gain. Plus just general architectural refinements.
Okay.
Then there's efficient algorithms and quantization.
Yeah.
Things like accurate quantized training AQT means using lower precision numbers like 8-bit integers instead of 32-bit floats for calculations. Less data to move, faster math.
Without hurting the model's quality too much.
That's the trick, yeah. Doing it accurately. Then there's a whole suite of optimized inference and serving techniques.
Like what?
Speculative decoding helps predict likely continuations, serving responses faster with fewer resources. Distillation is big, training smaller, faster models, like Gemini Flash, Flashlight, that capture most of the capabilities of a larger one, but are way cheaper to run.
So you train big, but serve small and efficient.
Often, yes. Batch inference processing lots of prompts together to keep the accelerators busy. It's a balance between latency and throughput. Disaggregated serving, using different specialized hardware for the initial processing, prefill, and the token generation, decode. And KV caching, saving intermediate calculations so you don't have to recompute them for every single token. Lots of clever engineering.
It sounds like optimization at every possible level, and the hardware itself.
Huge factor. Custom-built hardware. Google co-designs their models and their TPUs, tensor processing units. Their latest, Ironwood, is apparently 30 times more energy efficient than their first TPU.
30 times. That's massive progress just on the chip side.
It really is. They also focus on optimized idling, not just letting machines sit idle, but dynamically shifting workloads around to minimize the number of powered up but unused accelerators.
Smarter resource management.
Exactly. Their ML software stack compilers like XLA, kernels like Pallas, systems like Pathways, they're all crucial for translating the model code into efficient instructions for the hardware.
The software enabling the hardware performance.
Precisely. And underpinning all of it are those ultra-efficient data centers with that 1.09 PUE we mentioned, delivering way more compute per watt than just a few years ago, plus their water stewardship.
And finally, the clean energy aspect.
Right, their continuous clean energy procurement. That 30% drop in their Scope 2 emissions factor in 1 year, even while growing. That's huge. It shows they're actively decarbonizing their operations.
Okay, so putting this all together, what are the big takeaways, the implications of this study?
Well, I think the clearest message is about transparency and standardization. For these environmental metrics to mean anything, to be comparable, we need a standard, comprehensive measurement boundary like the one they propose.
Otherwise, it's just comparing apples and oranges, or worse, potentially misleading numbers.
Exactly. It hinders accountability, hinders progress. This kind of holistic view lets you see the real hotspots and incentivizes gains across the whole stack, not just optimizing one small part while ignoring others.
And while one prompt's impact is small,
Super small.
the sheer scale, billions and billions of prompts globally, means that continuing to chip away at that cost, making it even smaller, is absolutely critical.
It has to be. The scale demands it.
So really, this paper is kind of a challenge, isn't it? A call to action for the whole AI community.
I think so, yeah. It's advocating for adopting this kind of comprehensive measurement widely. We need to make sure that as AI gets more powerful, it also gets more efficient, environmentally speaking.
We need to tackle both challenges, AI advancement and climate impact, side by side.
Absolutely. So yeah, we've seen how Google's deep dive, their full stack approach, gives a much clearer, more actionable picture of AI's environmental cost in the real world.
And those huge reductions they achieved show it's possible. Significant gains are achievable if you measure properly and optimize relentlessly.
It proves the value of the effort.
So the final thought for you listening, if you're an AI researcher, an ML engineer, anyone deploying these models, what parts of this comprehensive measurement could you bring into your own work?
Even if you're not at Google scale, the principles apply.
Right. How could you get a better handle on the full footprint of your models? Could looking at it this way spark new ideas for optimization in your own MLOps pipeline? Something to think about.
It's a vital conversation for the future of responsible AI development.
Keep digging into those details behind the headlines. We'll be back soon with another deep dive.